Good day, everyone. We're going to wrap up this week, today and Friday, with a special use of differential equations. In particular, we're going to be studying problems and situations that involve what we call exponential growth and exponential decay. Now, you certainly would have studied this model when you were in Algebra 2, but probably never mentioned a differential equation or derivative back then. You probably just were given an equation that models population or exponential growth and exponential decay. But so we are going to study, though, a little bit about where that model comes from in this first video, and then we will solve some sample problems in the next video. Okay, so our objective today is to use differential equations, at least at the beginning of this lesson, to show you where the law of exponential growth comes from. So it all starts with this type of situation right here. It says the rate of change of a quantity y with respect to time is directly proportional to y. I encourage you to pause right now and think about how you learned to translate that sentence on Monday into a differential equation. And now let's take a look and see how I would do that. The phrase rate of change of y with respect to time, that is our derivative, dy dt. And what hopefully you saw a number of examples of on Monday was that phrase directly proportional means that the quantity that's directly proportional to y means it is a multiple of y. And for now, we're just going to make a general constant there, k. And so the rate of change, dy dt, is equal to a multiple of the thing it's proportional to, which is y. Now, we just use y in this situation here because that is the most common variable used for the dependent variable of in any math problem really. But you could probably see in other situations, maybe since this law most commonly applies to population growth, or very commonly does, you might see the variable p instead. So you might see the differential equation dp dt equals kp, or really any variable could be used. Now let's think about what this means here. This means that the rate at which something grows is proportional to how big it is. So just think about some situations we know that do that. One that I know most of you are familiar with would be, say, money in a savings account. So let's say you had deposited, let's say you had a starting balance of $1,000, right? And your bank pays you interest. Let's just keep it very simple. You get a payment of interest at the end of 12 months, so after a year. And let's say that after 12 months, the interest payment back to you was $10. So you gained $10 per 1 year in interest. Okay, now it makes sense then if someone else had a bank account and had $2,000 in it, and everything else was the same, interest rate was the same bank, everything, they should probably get more money back in a year. They should probably get $20 per year back because they had double the amount of money to begin with. So over here we have the quantity that you have, the dollar amount in your bank account, and over here we have the rate at which it grew in dollars per year. And so here's showing that the rate of change is proportional to the quantity, because if I double the quantity from $1,000 to $2,000, that also doubles the rate of growth as far as dollars per year goes. Okay, and the reason why this works is because we know that interest and so forth is percentage based, which means, so this looks like these are both getting 1% per year. Okay, so again, if we were to double it again, and someone else started with $4,000, they should have gotten $40 in a year of interest. Other things do that too. Populations do that. It doesn't have to be people. Maybe it's the population of a certain type of animal in a region or something. And it would make sense that the more the more of that animal that are present, the more the faster it will grow. Okay, so those are all examples of things where the rate of growth is proportional to the population size. Now, we're going to spend a little time here doing some calculus and showing what then is the explicit formula for the population, okay? And so here again, we have our starting point for the law of exponential, law of growth and decay, and that is it always starts with the rate of change of the quantity is proportional to the quantity. As we move forward here, you certainly, this is one thing I know for sure, you guys, on your AP test, if you were to see the phrase, the rate of change of y proportional to y, or really make up whatever variable you like there, the rate of change of p is proportional to p, you are expected to know this differential equation. You're also expected to know what we're going to derive on the next slide here too, what the result of this is, okay? What you need to know first is recognizing that this is a separable differential equation. I can separate the y's and the dy's from the t's. And the best way to do that is we're going to bring the dt to this other side. And dy is ky dt. It's almost like multiplied by dt here. And we're going to now divide by just the y. So we're going to divide by y here and here. So my separated equation is dy over y equals k dt. And we're now going to integrate each side. And hope on the left side you recognize this is a logarithm type integral. So the integral of dy over y is the natural log of y. And the integral of k, well, k is a constant, so the integral of dt is t. So this is going to be kt plus the integration constant plus c. And our goal is to get y by itself, of course. So we're going to now take e to the power of both sides. And on this side, e to the raised to the natural log of y, those cancel. So we just have y equals. And now remember the little bit of algebra on this side. Remember that this is e to the power of the entire quantity, kt plus c. So remember your algebra here. That really means this is the same as e to the kt times e to the c. And I'm just going to circle this and say, well, that's really just another constant. In this context, I like to rename that something else. So from now on, we'll just say, let's let e to the c equal the number a. And so from now, I'm going to write this as y equals a times e to the kt. And let's just circle that. That is our general solution of that original differential equation. Now let's make a couple of notes about the two constants there. You're going to be asked about that today in your homework a little bit. First thing is about that constant k. What do we know about it? You can trace that back a little ways and look at the differential equation that we started with here. And that, if I rearrange it just a little bit differently and actually solve for k for this in this context, it would be the rate of change of the quantity divided by the size of the quantity. So because of that, k is often referred to as the relative growth rate. Meaning, you know, it's what you would get if you divided the rate at which the quantity is growing, or like the rate of change of the population divided by the population size. Okay, so we call that the relative growth rate. The other thing is about this constant a. Now let's take a look at it here. And we can observe something about it. If I were to ask you, what is the starting value of y? In other words, what do I get if I'm at the very beginning of the study and the t is 0? Okay, so when t is 0, y would equal a times e to the 0. And we know that e to the 0 is 1. And so what we can observe here is the quantity A is really y of 0. Or we could just call that the initial value of y. Okay, it's y of 0. And so in a word problem, you might be given the initial quantity of the population or the initial value of the quantity, and that you know is going to be translating to the value A in this model here. Okay, well, we'll see in the next video where we do a couple of examples using the law of exponential growth and decay.